I'm Patty Simpson with Simpson Math. Let's learn about factorials. So a factorial is just another operation. Just like if you see a plus sign, you know that that means that you're going to combine the numbers. You're going to take 3 and 2 and put them together. That's an operation that tells you what to do with your numbers. Or, for instance, if you have something like a square root, you know that you're looking for, this is an operation where you're looking for a number that multiplies by itself to give you 16. A factorial is just another operation. And we show a factorial with an exclamation mark. This exclamation mark means factorial in mathematics. So a factorial is just the product of every number from 1 up to whatever number it is that's in front of your exclamation mark. That's all that factorial means. So this factorial, we read it as 7 factorial. And that 7 factorial, this exclamation mark right here, just means to take the numbers 1 times 2 times 3 times 4 times 5 times 6 times 7. I'm just going to multiply those numbers all the way up to 7. And then I stop there at 7. So I have 1 times 2 is 2, times 3 is 6, times 4 is 24. We're starting to get a little bigger now. 24, well, 5 times 6 is 30. Well, and times 7 is 21. So we could say 210. And then we multiply those two numbers together. So it ends with a 0. And you have 4. And 8 and 2 is 10. Carrier 1, 4, 5. So that equals 5,040 if we multiply all those numbers together. So 7 factorial is equal to 5,040. It's just the numbers 1 times 2 times 3 times 4 times 5 times 6 times 7. We can also write it in descending order. And most of the time we do. When we talk about factorials, most of the time we actually write them in descending order like this. We say 7 times 6 times 5 times 4 times 3 times 2 times 1. And then on bottom of this fraction, notice I have 5 factorial. Well, 5 factorial is just counting from 1 to 5, or we could count it in descending order starting at 5. 5 times 4 times 3 times 2 times 1. Now notice when we have that 7 factorial over 5 factorial, that here I have a 5 on top and a 5 on bottom. Those cancel, or they become 1. The 4 divided by 4 is 1. The 3 divided by 3 is 1. The 2 divided by 2 is 1. The 1 divided by 1 is 1. And I'm just left with 7 times 6. But let me show you another way to write this. Instead of writing it all the way out, I could have stopped. I could have written 7 times 6, and then this 1 times 2 times 3 times 4 times 5, or this 5 times 4 times 3 times 2 times 1, I could have written as 5 factorial. This means 5 times 4 times 3 times 2 times 1. This is the same thing as what I had written over there. Now, on bottom, I don't have to write that out. I just have 5 factorial on bottom. Notice it's the same thing on top as it is on bottom. So I could have just stopped. I could have written 7 times 6 times 5 factorial, and this 5 factorial divided by that 5 factorial becomes 1. So I have 7 times 6 either way, which gives me 42. As our problems get more and more complicated, this may be handy to do so that we stop at a number so that we can cancel out or simplify. Let's do another example. Here I have 7 factorial over 5 factorial and 2 factorial down there on bottom. So I'm going to use that same trick I just did, where I do 7 times 6 times 5 factorial. Because I know that this 5 factorial and that 5 factorial are going to cancel out. But I didn't keep going down to 2 times 1. So this 2 factorial is still 2 times 1. I have to have him on there as well. So this 5 factorial and that 5 factorial will cancel out, or they will become 1. But I still have a 7 times 6 over a 2 times 1. I have 7 times 6 over 2 times 1, which is just 2. Again, I'm going to simplify before I multiply. So this 2 can go into that 6 3 times. So now I'm just multiplying 7 times 3, which gives me 21. Let's do this one. Here, I need to do inside the parentheses first. So I have 7 minus 2, which gives me 5. And that factorial is on the outside. So it's 5 factorial. And there's still a 2 factorial there being multiplied. Now, I'm going to simplify again. So I have 7 times 6 times, I'm going to stop at that 5 factorial. And that's the same as what I had before. So the 5 factorials cancel, the 2 goes into 6 3 times, and I still have 21. We're going to use these factorials to help us with something called counting, where we're looking for how many different ways we can collect a group from a larger group. And we're going to use these factorials to help us with that. Let's look at a few more examples of factorials. So a factorial is just an operation that tells us to multiply all the numbers from 1 up to the number in front of that exclamation point. This means factorial. Now there are a few things that we need to know that we've just defined. We've defined 0 factorial to equal 1. So anytime we see 0 factorial, that's just equal to 1. And 1 factorial is also equal to 1. So just know those two are just both 1. But with 6 factorial, all we're going to do is take our numbers from 1 to 6 and multiply them. And you can go in ascending order, or you can go, usually we write them in descending order, where we say 6 times 5 times 4 times 3 times 2 times 1. Well, 6 times 5 is 30, and 4 times 3 is 12, and 2 times 1 is 2. So 30 times 12, well, 3 times 12 is 36. Put a 0 on the end of that. Times that 2 still. Double 360 and you get 0, 12, carry your 1, 6, 720. So 6 factorial is equal to 720. It's just equal to all those numbers below 6 all multiplying together up to 6. Here I have 12 factorial divided by 9 factorial. So I could count all the way down 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Or at this 9 factorial, if I stop at 9 and write it as 9 factorial, that means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So I can stop there. This is another way to write that 12 factorial. And I stopped here because I saw the 9 factorial on bottom. And now I have the same thing on top, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 1, as I do on top. Bottom and top are the same. So this divides to be 1, and it just leaves me with 12 times 11 times 10. Well, 12 times 11 is 2, and 1 is 3. 1 times 1 is 1 with a 0 on the end. 1,320. So when you can, if you can see below to stop at a factorial, it makes it a little bit easier to simplify that. As we begin to use our combinatorics formula, we're always going to be able to simplify it down until we don't have a denominator. Let's look at this one. Here I have 15 factorial over 3 factorial times the quantity of 15 minus 3 factorial. With all our order of operations, I'm going to start inside this grouping symbol. So I'm going to do the 15 minus 3 first, which gives me 12, and then that factorial is on the outside. And that's multiplying times this 3 factorial. Now, before I can multiply these two numbers, I have to recognize that this 3 factorial means 3 times 2 times 1. And I have to recognize that this means 12 times 11 times 10, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But I think what I'm going to do is take this 15 and make it stop here at the 12 factorial. Because if I were to keep going, this 12 factorial means it keeps going down. And this 12 factorial then is on bottom, so that the 12 factorial and the 12 factorial become 1. Now I still have this 3 factorial here, and that 3 factorial means 3 times 2 times 1. So I do need that here. I don't have a 3 factorial on top. So I need to write him out as 3 times 2 times 1. But I do like to simplify if I can, and in these when I'm doing the counting, I'm going to be able to simplify it. So we should simplify it all the way down to make it easier on ourselves. So 3 goes into 15 5 times, and 2 goes into 14 7 times. So now I just have 5 times 7 times 13. I've made it a little bit easier on myself. And I can do 7 times 13 gives me 21, carry 2, 7, 8, 9. And then I have times 5. Well, 5 times 91 is 545, so 455. So this factorial divided by those 2 factorials leaves me with 455. One more, I have 6 factorial over 6 minus 6 factorial. Again, I'm going to do inside the parentheses first. That leaves me with 0 factorial. So I have 6 factorial over 0 factorial. Remember that 0 factorial means 1. So I have 6 factorial over 1. Well, we saw earlier that 6 factorial was equal to 720. So this is really 720 divided by 1, which is just equal to 720. So 0 factorial is always just defined as equaling 1, as is 1 factorial, that is also just equal to 1. So there's a little more practice with factorials. Let's learn about combinatorics. So we're going to answer the question of how many. As we look at probability, we need to know the total number of outcomes that there are in certain experiments. And sometimes, even when it comes to the events, we need to know how many different ways we can get those events. So in order for us to be able to do the probability and find the probability, we need to be able to answer that question of how many. So here in counting, we're going to answer that. How many ways? How many groups? How many choices? And there are 3 different techniques that we're going to use to help us answer that question. The first one is called the fundamental counting principle. And in the fundamental counting principle, we'll use this when we have independent events, a certain number of choices for each one of those independent events. And in that case, we'll just multiply the number of choices in each case. So for instance, if we want to know how many different outfits we can wear, and we look at the number of shirts we have, the number of pants we have, and the number of socks we have, shirts, pants, and socks are all independent events as we choose each one of those. And so however many we have of each one will multiply together. Or another example might be if you're taking a multiple choice test and each one of your questions has a certain number of answers to it. And you want to know how many different ways could I fill out this test? Well, each question then is an independent event. And you'd have to look at how many choices there were for each question and just multiply those together to find out how many different ways. So for the fundamental counting principle, each one of our parts is an individual little event. Here, for permutations and for combinations, for both of these, we're going to have a large group of something, and we're going to be choosing from that large group, some of that group, or maybe all the group, but we're going to be choosing from that group. So in both of those cases, we have the same situation, large group choosing some. But in permutations, the order matters. And when we say the order matters, the reason the order matters is because each one of our places that we're choosing for is a place or a position. Like maybe I'm lining you up in line. Well, you know you want to be the line leader. Or maybe you're really keen on turning off the light, so you want to be second in line, so you get to turn off the light. Or maybe you want to hold Miss Simpson's clipboard, and so you want to be third in line. The position there matters where you are. That order matters. So when order matters, or we're arranging something, you know, the pictures on the wall look one way. When we arrange them, it looks one way, but if I switch them around, that's a completely different thing. The order there matters. So those arrangements and places or positions, we'll use permutations. But when the order doesn't matter, then we'll use combinations. So instead of choosing you to get in line, I'm just going to choose you for bonus points. Well, you know, you don't care if you're chosen first or last, as long as you get those bonus points. So when the order doesn't matter, or I'm choosing a group where it's just a group and everybody in it's the same, then we're going to use this combination to help us out. So we're going to use these three techniques to help us to answer the question, how many? Today we're going to talk about the fundamental counting principle. Now we can use this fundamental counting principle when we have different options and we want to determine how many different choices we have, or how many different options or opportunities that we have. So here's an example of that. Sarah wants to take 2 classes this summer, English and history. And there are 3 English classes and 2 history classes for her to choose from. Now notice that when she takes the English classes, she can choose those English classes, and whichever English class she decides to take, it's not going to influence her decision with her history. In other words, they're independent of one another, those choices are. And we're assuming that the times don't overlap for any of the classes. And she wants to know how many different schedules she can make. So we're just going to draw kind of a picture of what she can do with her schedules. What are her different options? Well, she could, she has 3 choices here with our English classes. Let's decide to label those 3 classes as English A, English B, and English C, because she has these 3 different choices of English that she can take. And maybe with English A, she decides that she wants to take history, the first history, we'll call it History A. But she could also choose to take the English A, and instead of taking it with History A, maybe she decides to take the other history class. We'll call that one History B. Or maybe she looks at that English class and decides she doesn't want to take it for whatever reason, so she decides to take the English B. Well, again, she could take that with the first history, or the History A, or she could take that same English with History B. And notice that the choices are independent of one another. Whichever English She can make her choice about English, and then she can make her choice about history. Last but not least, she has this English C, so maybe she decides she doesn't want to take English B for whatever reason, and she moves over to English C. Again, she has the choices to take English C with history A, or she can take English C with history B. So looking at it, she has 1, 2, 3, 4, 5, 6 different ways that she can create her schedule. Notice that what we have done is we really have 3 groups here. English A is one group, English B is another group, and English C as a third group. Because we have 3 options of our English, we have 3 groups. And in each one of those groups, we have 2 histories, or 2 different things in there. Now mathematically, we can represent that with multiplication. That's what multiplication says. It says that we have 3 different groups, or however many groups, with however many things in it. So here we have 3 groups of 2 things, which gives us those 6 choices. So the fundamental counting principle says that we can just take our different options and multiply those together to get the total number of things that we can create. Here's another example. Bailey has 3 pair of pants, 6 shirts, and 4 ties. And he wants to know how many days he can stretch that out and look like he has a different outfit on every single day. So we can determine how many different outfits he can wear by using that fundamental counting principle. This is the same as kind of like the English, where we have 3 different pair of pants. So we're going to have 3 groups with those pants. And in each one of those groups, we're going to have 6 shirts. Or we could say 3 times 6 equals 18 different things. Now that's just with the pants and the shirts. So he has 18 different outfits he can wear just by changing up his pants and his shirts. He can also add to that or make more outfits by then adding in the ties. Well, now we have 18 groups, 18 different outfits that we can wear 4 different ways. So again, we're going to use that multiplication, 18 times 4, to give us, well, that's 40 plus 32, gives us 72 different outfits that Bailey can wear before repeating himself. One more example, Todd has a sandwich shop that he decides to open, and with the sandwich shop, he's going to offer 5 different choices of bread, 8 choices of meat, and 6 choices of cheese. And we want to know on the menu how many different items can he put, how many different sandwiches can he offer. Well, 5 choices of 8 meats, so think of this as your groups, and this is how many are in it. So we've got 5 times 8, which gives us 40. And then now we have 40 different sandwiches that we can do just with the bread and the meat. By adding this choice of cheese to it, our 40 groups now has the 6 choices as well. So we have 240 different sandwiches that he can put on his menu. And today we're going to talk about counting techniques. In our last video, we talked about the fundamental counting principle, where we found the different ways that we could do things when we had independent events. In this video, we're going to be dealing with dependent events. So here's an example. Charlotte has 5 quilts that she wants to give to her 5 grandchildren. And she wants to know how many different ways she could choose the quilts to give to her grandkids. So let's think about that for a second. If she decides to give her first quilt, this quilt, to one of the grandchildren, now she only has 4 grandchildren to choose from to give the rest of her quilts to. So on the next one, she has 4 different options where she could choose. Then from there, now she's chosen 2 of her grandchildren, so she only has 3 grandchildren to choose from. So if she chose 2, then on the next one, maybe she chooses 3. So each time she has 1 less to choose from, 1 less grandchildren to choose from. So in order for us to determine how many different ways there are, we know that to choose the first one, she has 5 different ways she could choose that. On the next one though, there are just 4. So think about last time where we had our 5 groups, but now we just have 4 things in it. So we're going to multiply our 5 times our 4. Well, now we only have 3 different grandchildren. So we multiply it by 3. Now we have 2 grandchildren down to 1 grandchildren, or grandchild. So we're now, so these are all the different ways that she could choose to give her 5 quilts to her 5 grandchildren. If we do that multiplication, we see that we have 20 times 6 times 1, which gives us 120. There are 120 different ways that she can give her grandchildren, her 5 grandchildren, those quilts. Another way for us to write this in mathematics, when we have 5 times 4 times 3 times 2 times 1, is 5 factorial. I have another video on factorials to help you out if you want to learn more about factorials. Let's do one more where we have dependent events here. Here I have the letter tiles, like in Scrabble. I've drawn these letter tiles, B-S-T-L-E-A. And I want to put them down on the board, and I want to know how many different ways I could arrange those letters. How many different ways I can arrange them. Now, there may just be a few words that I could use, but let's just pretend that I can put them down in any order. How many different ways can I arrange them? Well, I have 1, 2, 3, 4, 5, 6 letters. So if I choose this letter, so the first one I have 6 choices. I could choose from any of those 6. Well, after I choose one of those 6, then I only have 5 letters left. Once I choose one of those letters, I only have 4 letters left, and then I have 3 letters left, and then I have 2 letters left, and I have 1 letter left. Another way for us to write this, when we have the whole numbers from 1 to our number being multiplied together, is as 6 factorial. When I multiply these out, 30 times 12 times 2, or 360 times 2, which is 720 different ways that I could arrange those letter tiles. And today we're going to talk about permutations and combinations. I'm going to make several videos, and this is just the first, to help us with a basic understanding of when to use permutation versus combination. So permutation, order matters. So we're going to use permutations anytime order matters. Combinations we'll use when order doesn't matter. Let me give you some examples. In our first example, a club is choosing 5 members for different positions, for president, vice president, treasurer, secretary, and historian. Each one of those positions is different. So when we are chosen, if the first one's going to be president, that is a different position than vice president. And so there the order matters, and we would use permutation. Permutation. Similar scenario, a club is choosing 5 members to sit on a committee. There, it doesn't matter if the member is chosen first or 5th. They're all going to go to the same committee and sit on the committee. So there, the order doesn't matter, so we would use combination. Here's another example. I'm going to choose 3 people from my class to give bonus points to. The first person I choose gets 10 points. The second person I choose gets 5 points. And the last person I choose gets 2 points. There, you want to be chosen first. The order matters. And so, therefore, here we would use a permutation. same example or a similar example, I'm going to choose 3 people again to get bonus points, and every one of the people, each person I choose is going to get 5 bonus points. There, you don't care if you're chosen first or if you're chosen third, as long as you're chosen. So order doesn't matter there, so we use combination. On our last one here, another example. Here I'm going to choose 5 dogs from the pound. In my first example, I'm going to take those 5 dogs home with me from the pound. Again, it doesn't matter if I choose that dog first or if I choose it 5th. All 5 dogs are going to get to go home with me. So therefore, order doesn't matter. This is a combination. In our last example, I'm going to choose 5 dogs, but I'm going to line them up. And I want to know how many different ways I can arrange them in line. Well, you know, spotted dog at the front is different than spotted dog at the back. And so therefore order matters, and that's a permutation. Now, it's a little bit confusing, this permutation and combination, especially because when I think of a combination lock, I think order matters there. Really and truly in the English language, those combination locks should be called permutation locks. So from now on, anytime you're locking up a bicycle or using a lock to lock up a locker, you should call that a permutation lock because order matters. And today we're going to continue our conversation about permutations versus combinations. We're going to look today at the formula for both permutation and combination. And we're going to see why the formulas work for each one. So last time in our video we talked about the fact that permutation we use when order matters, and combination we use when order doesn't matter. And we have the formula here for permutation, where N represents the number in our group, and R represents the number that we are choosing. So for this formula, it tells us that we're going to take the number in our group, take the factorial of it, and divide that by the number in our group minus the number we choose, the factorial of the difference there. That's permutation. Combination is almost identical. Has the same notation of N means the number in our group and R means the number that we are choosing. And it's the same idea where we take the number in our group, the factorial of it, and we divide it by the difference between the number in our group and the number we're choosing, the factorial of it. The only difference is we also divide by the number that we are choosing, the factorial of it. So it has one more little number in there. And let's see if we can find out why that is. So I have an example here where there are 4 friends: patience, temperance, honor, and charity. Oops, that makes 4. They're in a race, and we want to know how many different ways they can come in either first or second place. Now, because those places are orders, and the order matters there, being in first place is different than being in second place, we're going to use a permutation. So because order matters, we use permutation. And just to kind of get familiar with the notation here, our N tells us how many are in the group. And in this case, we have 4 friends, so there are 4 in our group. And the R is how many people we are choosing. In this case, we're only looking at first and second place, so that's two that we are choosing. So before we use the formula though, let's just look and see how many different ways they can come in first and second. Let's just go through and list all the ways that they can come in first or second. I'm just going to use their first initial to help me, and let's just look and see. Patience could come in first, and temperance could come in second. Or patience could come in first, and honor could come in second. Or patience could come in first, and charity could come in second. Those are all the different ways where patience could come in first. Let's do it with temperance now. Temperance could come in first, and patients could come in second. Notice that this is different than that because the places were different. Here, temperance could come in first and honor could come in second. Temperance could come in first and charity could come in second. Those are all the ways that temperance could come in first. Let's do honor. Honor could come in first and patience could come in second. Again, notice that that is different than this because their places are different. The order matters there. Honor could come in first and temperance could come in second. Or honor could come in first and charity could come in second. Again, this one is different than that one, even though it's the same people, because the order here matters. Charity could come in first and patience could come in second. Charity could come in first and temperance could come in second, or charity could come in first and honor could come in second. So those are all the different ways that they could win the race. So we have a total of 3 times 4, 12 different ways that these friends could come in first or second place. I'll show you with the formula here in a minute, but let's look and see. Same situation where we have the same 4 friends, but now Prudence's mother says, hey, you can choose 2 of those friends for a sleepover. So Prudence wants to know how many different ways she could choose 2 out of the 4 friends. In this case, the order doesn't matter. Whether they're chosen first or second, they still end up in the sleepover. So let's look at the different ways she could choose. She could choose patience and temperance. She could choose patience and honor. She could choose patience and charity. She could choose temperance and patience. Oh, wait a minute. This is the same as having patience and temperance over. Because the order doesn't matter, this group is the same as that group. So that's not another way. It's the same as that one. But she could have temperance and honor. We don't have that in the group. She could have temperance and charity. We don't have that one yet. She could have honor and patience. Oh, wait a minute. We already have honor and patience here coming over. She could have honor and temperance. Oh, wait a minute. We already have that one here because that's the same group. Honor and temperance, or temperance and honor coming over is the same thing. But we don't have honor and charity. And we have charity now with every one of our partners. So in this case, there are only 6 different options for Prudence to have to choose 2 of those people. So notice that when order matters, we actually end up with more possibilities. When order doesn't matter, we have less possibilities. With the formula, when we divide by this extra number down here, this r factorial, it makes our number smaller. Dividing by that number is going to make it smaller. So that's the reason that our combination has an additional number on the bottom. Now let me just show you quickly the formula for these 2 problems, and then in the next video I'll do some more difficult examples. So here I'm just going to plug in. Our n was 4. We decided it was a permutation because order mattered, and our r was 2. So everywhere I see an n, I'm going to plug in that 4. So I had 4 minus the 2 factorial. So remember that factorial, what I'm doing is taking all of my numbers and just multiplying from 1 up to this number. So this 4 factorial means 4 times 3 times 2 times 1. On the bottom here I have 4 minus 2, or 2 factorial. I'll go ahead and write that out. So that 4 times 3 times 2 times 1 over this factorial means 2 times 1. This 2 divided by that 2 gives me 1, and 1 divided by 1 gives me 1, so that I end up with just 4 times 3, or 12 different ways hey, we found all 12 of those ways. In this case, we'll use the combination formula because here order didn't matter. But same idea, we still had 4 people in our group. We're choosing 2 of them. So here I put the 4 factorial on top. My r there is 2 factorial. And then my n minus my r, and I'm going to find the factorial of that. So that I have 4 times 3 times 2 times 1 on top. On bottom I have 2 times 1, and then I have that times 2 factorial, or 2 times 1 again. Here this 2 and that 2 become 1. This 1 and that 1 are 1. This 4 divided by that 2 is 2. And 1 on bottom just gives me a whole number. So on top I here have 2 times 3, which is 6, divided by 1 just gives me the 6. There are 6 different ways, and sure enough, there were 6 different ways for us to invite our friends over. So hopefully that gives you a little more idea of when to use and why the formulas work the way they do. For combination, you just have one additional number that you're dividing by to make that number smaller, because when order doesn't matter, we have less choices. Today, we're going to work on using the formula for permutation and combination. In the last few videos I've done, we talked about when to use permutation and combination and why the formulas look like they do. In this video, I'm just going to do some examples where I'm using the formula. So in permutation, we have our formula of m factorial divided by n minus r factorial. And here I have some numbers that I'm just going to plug into the formula. So in this case, I have 15 is my n, and I'm choosing 3, and for some, they need to be, the problem shows that their order matters in this case. So now I'm just going to plug it into the formula so that I do 15 factorial over 15 minus 3 factorial. I did another video on factorials. Remember that all that means is that we're multiplying our whole numbers from 1 up to n. In this case, is 15. So that 15 factorial, I'm going to do inside the parentheses here where I have 12 factorial. But this 15 factorial just means 15 times 14 times 13 times 12 times 11, all the way down to 1. 12 factorial means the same idea, where I do 12 times 11 times 10 all the way to 1. I stopped here at 12 because on the bottom I also have 12. Now I could write out 12 times 11 times 10 times 9 and do the same thing on bottom, but since this number 12 factorial is the same as that number 12 factorial, when I have the same thing on top and on bottom, that divides to equal 1. So I can make those just be equal to 1. Now, all I'm left with is 15 times 14 times 13, or 2,730. Here, I'm going to just do another example where I have a permutation with 20 and I'm choosing 5. Again, order mattered somehow in the problem. So I have my 20 factorial on top and 20 minus 5 factorial on bottom. I do inside the parentheses first. And now this 20 factorial is just 1 times 2 times 3 all the way up to 20. Again, I'm going to stop at 15 factorial because the bottom has 15 factorial. So this number on top is the same as this number on bottom. So those two are just equal to 1. And on a calculator, I multiply 20 times 19 times 18 times 17 times 16, or I just multiply those out, and I get 1,860,480 different permutations. For combination, just adds one little step into it. Still have the number in our group and how many we're choosing, so that I could write my combination with 18 choose 6. You may also see this written, another notation for that is 18 choose 6. This always means that we have a combination. So now I'm going to do this, just fill it into the formula, so that I have 18 factorial over the 6 goes in place of r, and then n minus r, 18 minus 6 factorial. Now, I'm just going to do inside the parentheses first. Now it's just a matter of doing the arithmetic. So that I have 6 factorial, and inside of here I have 12 factorial. This is a little bit trickier than down there, but I'm still going to write this out the same way, where I do 18 times 17 times 16 times 15 times 14 times 13. When I get to this point, this 12 factorial, just like before, this 12 factorial here and this 12 factorial on bottom are going to cancel, are going to reduce to 1. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. That's what that 6 factorial means down on bottom. So now I could multiply out on top and multiply out on bottom and then look for ways to simplify at that point. Or I could just simplify it to begin with. So I'm going to do that. I'm going to look for ways to simplify it. Notice that 6 times 3 is equal to 18. So instead of writing this whole thing, I could have written 18 times 5 times 4 times 2 times 1. So I'm going to take the 6 and the 3, which equals 18, and this 18, and divide those out to make it 1. I'm going to do some more reduction. This 5 can go into 15 3 times. The 4 can go into 16 4 times. And this 2 could either go into the 4 2 times, or it can go into the 14 7 times. Either way. Notice I'm only left with 1 on the bottom. And all whole numbers have 1 on the bottom. So in each one of these, you should be able to reduce it down so that only 1 is on the bottom. You should be able to simplify it all the way down to that. So now it's just a matter of doing this multiplication. What I'm left with is 17 times 4 times 3 times 7 times 13. So with a little multiplication work there, I determined that that's 18,564. One last problem, one last example. Again, I've got my combination is 14, choose 3. Or you may see that written in some places, 14, choose 3. And again, my 14 factorial goes on top. The 3 factorials on bottom, and 14 minus 3 factorial is also on bottom. So that 14 factorial, let me do it inside the parentheses first, so that I have 14 factorial over 3 factorial and 11 factorial. So that 14 factorial again is 1 times 2 times 3 all the way up to 14. Or I could write that 14 times 13 times 12 times 11. Now again, I'm going to stop there because I have this 11 factorial on the bottom, and this and that are the same number, so they reduce to 1. I still have this 3 factorial on the bottom, so I'm going to rewrite that as 3 times 2 times 1, because that's what that factorial means. Now in here, I have 3 times 2, which you notice is equal to 6. So I could take that 6 and divide it into 12. Or you could just take 3 and divide it into 12 and get 4, and 2 and divide it into 14 and get 7. Either way, I'm going to do it this way. 3 times 2 gives me 6. 6 goes into 12 2 times. Notice I'm only left with 1 on the bottom. In each one of these problems, I should be able to simplify it down so that I'm only left with a 1 on the bottom. Now I just need to multiply 14 times 13 times 2 so that I end up with 364 combinations. So order did not matter there. Let's look at some combinatorics examples. So in all 3 of these questions, it asks us at the end how many different ways or how many different things can we have. When we have that question of how many different ways, we know that we're looking at a counting or a combinatorics problem. And we know we have 3 different methods for solving the problem: fundamental counting principle, permutation, or combination. So we need to decide which we're going to use and then solve it. Here's our first one. A mechanic has a list of 10 customers, but only has time to work on 4 cars. How many different ways could the mechanic choose the 4 cars? So we have a group of 10 cars and we're going to choose 4 of them. When we have a group and we're choosing some, we know that's either a permutation or a combination. So then we ask ourselves, does the order matter? Do we care if we're the 4th one on the list or if we're the first one on the list? As long as we're on the list to get our car fixed, that's all that matters. So order here doesn't matter. We just want our car fixed. So this is a combination. So we're going to work with the combination formula where we have a combination, we have a total of 10 cars, and we're choosing 4 of them. We can also write that with this notation where we have 10 choose 4. This is just another notation for combination. It's only for combination, but this is another way to write 10 choose 4. Notice there is not a vinculum. It's not a fraction. It's just another notation that lets us know this is a combination. That's 10 choose 4. Then we're just going to use our combination formula where we put the 10 on top, factorial, over 10 minus 4, factorial on bottom. And since it's a combination, it also has the 4 factorial on bottom. Now we simplify. Let's start inside the parentheses. So inside the parentheses first, 10 minus 4 gives me 6 factorial. And then on top, I have 10 factorial. Remember, I can't multiply this until I take care of the factorial. That factorial is an operation I have to take care of next. So I have on top 10 times 9 times 8. Now I want to stop at the larger of these 2 numbers so that I can simplify and cancel those 2 out. So I'm going to stop at this 6 factorial. I could count it down, 6 times 5 times 4 times 3 times 2 times 1. Or I can just stop it at that 6 factorial and know that this 6 factorial and that 6 factorial are going to become 1. This 4 factorial, though, is not going to cancel out. So I need to multiply it so that it's 4 times that exclamation mark means it's 4 times 3 times 2 times 1. Make sure to count that one down. It is true, though, that we should, every single time we have a combination, be able to cancel out everything in the denominator. So this should divide into everything on top. Let's see if we can figure that out. So 4 goes into 8 2 times. 3 goes into 9 3 times. This 2 could go into the 10, or it could go into that 2, whichever one you like best. I'll do it into that 2. So notice that 4 times 2 made 8, so it just canceled out that 8. So then I'm left with 10 times 3 times 7. But maybe you were left with this 2 went into that 10 5 times, so maybe you had 5 times 3 times 2 times 7. We'll end up with the same answer either way. Now I just multiply. 3 times 7 is 21, times 10 is 210. So there are 210 different ways that he could group those 4 cars out of the 10 to put on his list to fix the cars with. Here's another example. A mechanic hosts a car show and 10 cars enter. How many different ways could the mechanic give first, second, third, and fourth places? Again, we have 10 cars that we're going to choose 4 from. So this is another either permutation or combination. Then we just ask ourselves, does order matter? Well, in this case, getting a first place or a second place are different. These have different places to them, different arrangements, or each position has a different title to it. So the order here does matter. So this is a permutation. And for permutation, we say 10, it's still choosing 4. So here we have our permutation of 10 and 4. So again, I have 10 factorial on top, but on bottom, I just have the 10 minus 4 factorial. We don't add the other 4 factorial there. Now I just multiply it out. This is 6 factorial on the bottom and 10 factorial on top. So I'm going to count down to 6. 10 times 9 times 8 times 7 times 6 factorial. This 6 factorial and that 6 factorial become 1. I have a little more math to do this time. I have 10 times 9, which is 90, and 8 times 7, which is 56. So there's a 0 on the end. 9 times 6 is 54, carrier 5. 9 times 5 is 45, plus that 5 makes 50. So there are 5,040 different ways that the mechanic can choose those 4 cars to give places to. Last one. A mechanic is fixing a car that has an alarm. The alarm has 10 up-down switches that make the alarm. How many different alarm codes can be made? This time we don't have a group of 10 cars that we're choosing a few cars from, nor do we have a group of alarms that we're choosing a few from. Instead, we have independent events happening here. We have these up-down switches that make the alarm. So picture what's happening. If you can have 1 up and 9 down, and that's one alarm. Or you could have 1 down and 9 up, and that's a different alarm. Or you could have an up, down, up, down, up, down, up, down, and that's a different code for the alarm. And we want to know how many different codes are there. So each one of those switches is an independent event that's occurring. So we need to ask ourselves, how many choices are there for each of those independent events? Well, the first switch has 2 outcomes, on and off, or up and down. So the first switch has 2, the second switch has 2, the third switch has 2, and we're really doing that for 10 different switches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each one of the up-down switches is its own little event that's independent from the others, and we're just looking at how many outcomes there are for each of those events. Now we do a little multiplication. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, 64 times 2, 64 times 2 is 128, 128 times 2 is 16, carrier 1, 4, 5, 256. Let's do this times 4, these guys, and let's make that last bit times 4. So 256 times 4, well 4 times 6 is 24, carrier 2. 4 times 5 is 20, with the 2 carried is 22, carrier 2. 4 times 2 is 8, 9, 10. So there are 1,024 different ways that we could set that car alarm. So this is how we deal with our combinatorics. When we ask how many different ways, we're looking for those three options. If we have a big group we're choosing some from, it's combination, permutation. Ask yourself, does order matter? If you don't have a big group that you're choosing a few from, look for the number of choices there are for each one of the events and use that fundamental counting principle. Math made simple, it's Simpson Math. Thanks for watching.